Hello viewers, in physics here, physics paper 2, we are now looking at optical instruments. I want us to discuss these optical instruments. We have more than 5 optical instruments. To mention, we can always have the human eye. We shall talk about the microscope. We shall talk about the telescope. We shall talk about the camera. That would be commonly the lens camera. And then we shall talk about the projector lantern. All these ones are optical instruments. Only that what is so commonly asked here, these two, the telescopes and then telescopes and the microscopes. Maybe let us discuss one by one. I want us to have the human eye. In the human eye, for us, we don't go as far as the biology goes. In as far as the human eye is concerned, we shall just know what is being needed, what is required, what is asked, like that. And for this other human eye, we shall only talk about the eye defects and so on. The parts of the eye where we commonly have interest are very few. Just talk about the lens, that eye lens, and then talk about where images are being formed, because physics is for it is interested in images. Where are we forming the images? How are these images formed? Look at this being the retina. This is the retina of the eye. Retina of the eye. That is that one does the same purpose. It has the same function as the film in the camera, like that. Retina. That is where the images are being formed, like that. There is what we call accommodation of the eye. We shall be discussing that, but let us now talk about the eye defects. The defects of the eye. We shall talk about long-sightedness. A long-sighted person is that person who can only see things that are very far, and he cannot see those ones that are nearer. That is a long-sighted person. Images that are very far, or objects that are very far are seen well, but those ones that are nearer cannot be seen clearly. That is a long-sighted person. Meaning that if this is the eye of a long-sighted person, talk about this one being the eye of a long-sighted person. The distance from the lens up to the retina, that distance, we always call it the length of the eyeball. Length of the eyeball. when we collect light from infinity, we expect images to be formed at the focal plane, something like that. What happens, it will mean that the distance between the image and the lens becomes the focal length, like that. So it will mean that when light comes and then incident on your lens, instead of converging at the retina, it converges beyond the retina. So this is where the image is formed. Actually, the distance from here, maybe from the lens, like that, up to where the image is formed, it becomes the focal length, like that. Here the focal length is the focal length is too long compared to the length of the eyeball. The focal length is too long compared to the length of the eyeball. This is what brings about this long-sightedness. A person is in that state where the focal length is too long compared to the length of the eyeball. The image is formed beyond the retina, like that. How can we correction? How can we correct this other defect in people's eyes? It would mean that if I wanted to remove this, this defect, I need to bring in some other lens. This is the eye, and this is the lens, like that. I'm correcting light from infinity. It would mean that before I serve this other lens, I need some other lens that will try to converge. See, when I put in a converging lens, it will first of all converge this light. It will converge it a bit. See, preventing the other effect of going so far. So it's like as if I'm converging it 2 times. I converge it first, so that by the time it reaches the other lens, it is converged more. So in the correction of the long-sightedness, you need a converging lens. So a victim who has long-sightedness, always the doctor must give that person spectacles that contain converging lenses. So I converge it first. When light comes, it passes through my spectacles. It has a converging lens. It converges it first. Then by the time it comes to my eye, it is converged more, so that I prevent it from going far. I prevent the image from going far beyond the retina. So at this time, it will just come and converge at the retina. So this person can now view like a normal person. This is the retina, and this is the retina. Did I talk about this one being the focal length now? The F is now here. The other time the F was so long compared to the length of the eyeball, like that. For a person to view normally, the focal length must be equal to the length of the eyeball, like that. So I'm correcting light from infinity, just like that. Let me talk about the short-sightedness. Short-sightedness, like that. A short-sighted person can only view things that are very near, and those ones that are very far, that person cannot see. Why? It is because this time around, from this other diagram, if I just correct light from infinity, like that, always the image does not reach the retina. Images are formed before the retina. So when I talk about this other distance from the image up to the lens, that distance becomes the focal length. Yet the other one is the length of the eyeball. the length of the eyeball is too long compared to the focal length of the eye, the retina is here, like that. That person will only see things that are very near and not those ones that are very far. How do we correct? Correction. Because that person wants the images to be extended a bit, you can't give that person a converging lens. You will first provide that person with a diverging, such that whenever we collect light from infinity, it will first a bit be diverged. See? Diversion would mean that this time if it is diverged, it would mean that this time around that it can be thrown more beyond where it was. You see? So we are throwing it beyond. That's how we can enable you to view objects as any other normal person. Actually, for you viewing images, like I will one time tell you that person who's putting on spectacles does not view objects. That person views images, like that. This is always a straight line. This is always a straight line. This is always a straight line, like that. That person sees images there. A person who puts on spectacles does not see objects. That person sees images, like that. So it would mean that this other now becomes the retina. This one now becomes the focal length. Now the focal length is equal to the length of the eyeball, like that. But this is a diverging lens. Diverging. Or you can call it a concave lens. And this in this other one here, we made the corrections on the convex. This is a convex lens. Convex lens. Or the other name is a converging lens. Like that. When the eye is in the action of viewing different objects, what it does, it commonly changes its focal length. The focal length variation in the focal length of the eye, the variation of the focal length of the eye such that it can view different objects. When you blink your eye, the moment if I wanted to look at this other duster, I can't look at this duster at the same time as I'm looking at the other box of pieces of chalk. When I look at this other duster, if I want to look at the other box, I have to blink. That blinking shows that I'm varying the focal length. By all means, you have to blink. By all means, you have to vary the focal length so that you can view some other object, like that. You can't look at this at the same time looking at the other before blinking. When you blink, you are varying the focal length. That other process of doing that is called accommodation. The accommodation of the eye is the variation of the focal length of the eye for it to view different objects, like that. Gives us, I think that would be enough with the human eye. I want us to move on to maybe we should talk about some other terms used. In these terms used, we have already looked at the accommodation. I have defined the accommodation. Accommodation is the process by which the eye changes its focal length. Actually, the eye lens changes its focal length such that it can view different objects or different images. Variation of the focal length of the eye becomes accommodation. I want to define particular terms here. I want to talk about a near point. And then of course some people will always ask you a far point. But this is the commonly asked near point. Somebody tells you that to define a near point. Then we shall tell you how to define the least distance of distinct vision. Least distance of distinct vision. Least distance of distinct vision. Then talk about near point, far point, least distance of distinct vision. We shall talk about the visual angle, like that. Sometimes used in your optical instruments. Near point. If this is my object, I want to view almost all details on this other object. But when I put it far, I can't view all the object's details well. I can't view all the object's details well. So if I can't view all the object's details well, then let me bring it near and see. When I put it just near my eye, still the details are not seen clearly. You will be trying, you will try out that. It would mean that there must be a suitable distance where the object's details are seen clearly. See? If this is the distance, then if this is the distance for my eye, if this is the suitable distance for my eye, it would mean that this point where this other object is what I call a near point. A near point. Let me say that this is the eye. If that is the eye, I'm putting particular writings on a particular paper that is far from my eye, and I can't see the details well. After asking that question that the details are not seen well, then let me bring this other piece of writing near my eye. Again, the details are not seen well. I try to extend it somewhere, and I find out that at some other distance here, the details are seen well. The position where the piece of paper with writings, for instance, this other one was maybe student, but the details are not seen well. Even here, and the way I'm seeing student is like as if I can't see some other words, but at this other position, I'm seeing the word student. At this other position, where the wordings can be seen clearly, this one is called a near point. So students, if you wanted to define a near point, is any point from the eye where all the object details, where all the object details can be seen clearly becomes the near point. Now the distance between the near point and the human eye is the least distance of distinctive vision. Distance from the near point up to the eye becomes the D. It is the least distance of distinctive vision. So you can have it as the distance from the eye, distance from the eye to the near point, Or somebody can talk about the distance at which all the object details can be seen clearly. Like that. So, that one pushes us to what we call the visual angle. Every object you want to see has an angle it subtends to you. It throws it to you. I want to see this duster. This duster gives me a particular angle at which I can see it. I want to see this piece of chalk. It gives me a particular angle at which I see it. The angle subtended by the object or the image. Sometimes we see images. So the angle subtended by the object or the image becomes the visual angle. And the visual angle, is the angle subtended by the image or object if it is subtended to the image, if it is subtended by the image, then that one would be aided eye. But if it is subtended by the object, the eye would be unaided. I will explain the difference between unaided eye and the aided eye. The angle subtended by the image to the aided and unaided eye, respectively. Or you can simply say angle subtended by the object to the human eye, and that would be all. Angle subtended by the object to the human eye. That one is okay. Like that. Relationship between the angle subtended by this other visual angle and the distance, the relationship between the visual angle and the size of the object or size of the image that you are viewing, like that. Imagine, I don't know whether you have imagined this so far, a particular number of trees being in line. If I had I had different trees, they are of the same size. These are trees of the same size. But to some human being that is somewhere here, these trees are seen. These trees are seen with different sizes. They are trees in line, but the tree that is near this person looks as if it is bigger compared to these ones. These ones look smaller. Maybe you can, if you can visit any forest and try to observe that the tree that is near someone is bigger compared to the other one that is far, like that. It just appears, because it is not true. It just appears to be bigger, the other one being smaller. Why? Because this one subtends a large visual angle compared to these ones. Yes, seconded by that, and then finally this. The visual angles are different. So the bigger the visual angle, the bigger the size. The bigger the size of the object you are seeing. Whenever the object subtends a big visual angle, it looks bigger. Whenever it subtends a smaller visual angle, it looks smaller. That is, it appears. Let me not use that word, looks. It appears to be smaller. It appears to be larger, like that. So the bigger the visual angle, the bigger the size. Yes, if I had maybe this one being the tree with a particular height h, like that, if this is theta, of which theta is the visual angle, I look at this other distance, maybe d. I want to talk about tan of theta. This other tan of theta becomes h over d, like that. It would mean that what happens that for small, if the angle is so small, for small angles, what is true? The tan of theta approximates to theta, meaning that I will be having theta being equaling to h over d, over h being equaling to d theta. If d is a constant, then it would mean that h is directly proportional to theta, and that is the relationship. The size of the object is being determined by the visual angle. The size of the object is always determined by the visual angle. So the bigger the visual angle, the bigger the size of the object. The bigger the visual angle, the bigger the size of the object. That would be the human eye being discussed now. That one now pushes us to microscopes as the second optical instrument. Microscopes. Microscopes. Like that. Is an instrument being designed to view nearby objects. Whenever you use a microscope to view blood cells, then you are using it in a right way. Because we therefore say that it is being used in normal use. That is normal adjustment of the instrument, normal use, like that. But whenever you use a microscope to view distant objects, that one it would mean that you are using it. You are not using it in its normal use. So there we say that the microscope is not in normal adjustment. Whenever a microscope is in normal use, the image will always be formed at a near point. So every time you strain it to do what it does, what it is not supposed to do, then it is not in normal use, of course. But whenever you use it to view what is supposed to do and then it would mean that it is in normal use, like that. So that's where we got those other words, normal adjustment, when not in a normal adjustment. So microscope can either be in normal adjustment, can either be used in normal adjustment, or when not in normal adjustment. Whenever the microscope is in normal adjustment, its images are formed at a near point. You want to use a microscope to view blood cells, to view small bacteria. There it is in normal use. So we expect the image to be formed at a near point. But we never use it when it's not in normal adjustment. Then the images will be formed at a far point or at infinity. Actually, we forgot to discuss what a far point is. A far point would be any point beyond which the object's details cannot be seen clearly. That is, a point beyond which. So if this is my near point, any point beyond my near point becomes the far point. So the object's details cannot be seen clearly. Some student may ask then about when I put it near here and the objects cannot be seen clearly. Still, that one becomes a far point. Any point beyond which the object's details cannot be seen clearly, that one becomes a far point. We are going back to microscopes. These microscopes are divided into one. Talk about the simple microscopes, and then two shall talk about compound microscopes like that. Commonly, what examiners want from these is to determine the angular magnification. We shall discuss what an angular magnification is and the linear magnification is. Actually, I want to define angular magnification definition, some of the terms that are used in microscopes. I want to talk about angular magnification, angular magnification, capital M. The other magnifications we have been dealing with are linear magnifications, the V over U. Those ones are linear magnifications, small m. This is the angular magnification. The other name given to it is magnifying power. So any examiner will always ask you, define magnifying power of a microscope, define angular magnification of a microscope. The definition is the same, like that. Angular magnification. I want us to use this other object because we shall always tell you, I have already defined the visual angle, but if I want to use this object, I want to view this other object like that. This object has an angle, it subtends to my eye. Yes? If that angle, this object has an angle, it subtends to my eye. I want to name that angle theta. Let me name it alpha. This alpha is the angle subtended to my unaided eye. It is the angle subtended to my unaided eye. The eye is not aided. When I say that the eye is not aided, I mean that I have not used the spectacles to see. I have not used the microscope to see, so I'm not aiding my eye. I'm not using a telescope to see, I'm using my naked eye. That's why I'm naming it unaided eye. But in some other books you will see people saying eye with no instrument. With no instrument. Eye with no instrument. Unaided eye. So this duster is subtending my the duster is subtending an angle to my unaided eye. Now, if that angle is alpha, then let me use spectacles. I just wear spectacles and then view the same duster. This duster will no longer be an object now. What I will be viewing using my spectacles would be an image. So the image subtends an angle to my aided eye. It is now the image subtending an angle. Whenever I put on spectacles, it is an image subtending an angle. But with no spectacles, it is an object. So I want you to quote that one clearly. People using spectacles to see, for them they don't view objects, they view images. So images subtend an angle to their eye. But whenever using your naked eye, it is the object that is subtending an angle to your eye. So I'm wearing spectacles. So the duster is subtending and the image of the duster is subtending an angle to my aided eye. If that angle was alpha prime, the angular magnification now becomes the ratio of this alpha prime to alpha. Ratio of the angle subtended by the image to the aided eye to the angle subtended by the object to unaided eye. Let me repeat. The angular magnification or magnifying power is the ratio of the angle subtended by the image to the aided eye, or what the eye is an instrument, to the angle subtended by the object to unaided eye, or what the eye with no instrument. That's how we define it. I have defined it. You can even write it and then write it in your box. So that is actually the common term. Now I want us to start from simple microscopes. Simple microscopes. To introduce these simple microscopes, for them their structure is made up of one lens. One lens, and that lens is a converging lens. Yes, we have only one lens and the lens is converging. I want to look at it when it is in normal adjustment, normal use. That is what students can now understand. Normal adjustment. Like that, when it is in normal use. When it is in normal use, we expect the final image to be formed at a near point. That is, now you will recall, I want us to recall, just if this is the lens, if we can move with this, then each and everything will be okay. This is the converging lens. I want to look at this one being F. I want this one maybe being into F. If it is a mirror, this is a C. But if it is a lens, it becomes a 2F, like that. The distance from here is the same distance up to there, and then you have a 2F there. There are only 2 points of interest. Whenever you want your image to be formed at a near point, if you want it to be formed at infinity, you put your object at F. You will always put your object at F if you want your image to be formed at infinity, because light will be coming from that incident on the lens, and then let it go through F. And then let us have some other light from that. See, these other lines will be parallel. That is, if this distance is the same distance here, the lines will be parallel. and when you try to extend it, then the other side, they will still be parallel. So the image here will be formed at infinity. Yes? So whenever we shall be talking about, whenever we shall be yearning to form our image at infinity, just know that the object that we are dealing with must be put at F. But if we are yearning to have our final image at near point, yes, you will always, if this is F, this is 2F, the other one is F, and this other one here is 2F, we shall just put it here. We always put it in between F and the pole of the lens. We just put it in between F and the pole of the lens, so that whenever light comes from here up to there, it passes through F like that. Then from here it goes. This time around you see that it's like as if they are it is diverging the other side. It would mean that the others, when I come and continue this, they just converge, so that I form a particular image here. See? Like that. So I'll be forming my final image at a near point whenever the object is in between F and the pole. But whenever I want it at infinity, then I'll be forming it I'll be putting the object at F. The moment you have these two ideas, then you are going to be able to draw the ray diagrams that you are going to be using in microscopes and telescopes. This is the basis I'll be showing you, and this other one here now becomes the basis. So I want us to have a simple microscope when in normal adjustment. I say that when it is in normal adjustment, we are forming the final image. We are forming the final image at near point. So what happens that if this is the lens like that, let me have F here. Of course, I'll be having F there. Then I think that is what you have. Then this is 2F, no problem. The other one is also 2F, like that. I want to form it at a near point. It would mean that where shall we put the object? The object will be put in between. In between does not mean in the middle. And for me, I'm putting anywhere in between. Anywhere in between, like that. Incident on the lens, let it pass through F. Like that, and then let us have light coming from that, and then diverges like that. Then when I try to extend this side, you must use a ruler here. Just use a ruler to extend, because this other one here must be in straight line like that. Even this must be in straight line. So you practice using your rulers where these ones intersect. We form a particular image. Let me say that the height of the object was h. See? And let me say that the height of this other image was maybe capital H. Like that. So there is a particular angle subtended. Someone is viewing from here. So there is an angle subtended to this other person's eye. By the other final image. So let me have this one as alpha prime. It is the same angle that is here. Alpha prime, like that, no problem. Now if you wanted to drive the angular magnification, because we discussed earlier that angular magnification, capital M, is the ratio of the alpha prime over alpha, where alpha prime becomes the angle subtended by the image to someone's aided eye, and the alpha becomes the angle subtended by the object to someone's naked eye. It would mean that your task is to find alpha prime and then alpha, and then substituting. You have got the derivation. What happens is we tell you that extract out that box for the object and be as if for it is just separate. That is how we will do it if we want it to be perfect. Extract out that triangle for the aided, for unaided, this other here. So this one becomes, you are viewing your object using your naked eye. This is H, like that. What would be the distance from here to here? That distance will be D, the least distance of distinctive vision, because the object you are seeing all its details. The object you are viewing all its details, and it would mean that where it is a near point. So this distance becomes the least distance of distinctive vision. We discussed that earlier. It would mean that I can have tan of alpha being equaling to opposite of adjacent, like that. And for small angles, do you know what that means? For small angles, you find out that this other tan of alpha approximates to alpha. It means that alpha becomes H over D, like that. So the alpha is H over D. Now the task you have is to find the alpha prime. Now the alpha prime will be got from the diagram that I have. What is the distance? If this is alpha prime, I'm considering the other triangle now. I have that tan. So this is unaided here. This is unaided. And I'm now looking at aided eye. That is when I'm using my microscope. The microscope now becomes the instrument. I'm using the aided eye. What happens that I have a tan of alpha prime. This tan of alpha prime becomes H over which distance is from here to here. That distance is also D, because this other image is seen with all its details. The real reason as to why I extracted out this is not to confuse people, because I was able to, I could put a D here, but I said I should not put it, I should not confuse people. People will start wondering why this is a D and also this one is a D, yet the distances are different. So whenever you are not using an instrument, extract out that one where you are not using an instrument. Then the diagram helps you to find the alpha. The diagram helps you to find the alpha, and then the diagram helps you to find the alpha prime, and the other one of the aided. I just have it ideally that whenever I'm using the unaided eye, I just extract it out. If you can understand that, then each and everything will be okay. The tan of alpha prime now becomes H over D. I'm saying it is D because the image details is seen clearly here. It would mean that this is a near point where the image is formed. Is a near point, and we say that the distance in between the near point and the instrument becomes the least distance of distinctive vision. It would mean that for small angles still, the alpha prime, I will now approximate the tan of alpha prime. Tan of alpha prime approximates to alpha prime. Therefore, alpha prime is simply H over D. Now, because you have alpha prime and alpha, you can find the angular magnification now. Alpha prime over alpha are giving us the alpha prime is H over D, but the alpha is H over D. So angular magnification becomes H over D. Now times D over H. Like that, the D is leaving, and I mean with H over that. But remember, from linear magnification, this other H over H, all these ones are heights of objects and images. So with linear magnification, you will remember that this is a particular linear magnification. linear magnification, I want you to recall, maybe let me try to derive it, that I have 1 out of f being equal to 1 out of u plus 1 out of v, like that. But when I try to multiply through by v, I'll be having that, and then v. So this other thing now becomes v over u, and then plus 1. But v over u is a particular magnification. You have a v over f being equal to magnification plus 1. So the linear magnification now becomes a v over f minus 1, like that. So this is a particular magnification. It is a linear magnification. Yes, the h, because this is the height of the image, and then this is the height of the object. So it's a magnification. So it would mean that instead of writing that, I can simply just write magnification being equal to v over f minus 1. But this v in microscopes becomes the distance of the image, yet the distance of the image here is a d. So in instruments here, for us, we shall not be using these v's, we shall be using d, like that. So it is d over f minus 1. Now this one becomes the angular magnification of a simple microscope in a normal estimate. It becomes the angular magnification of a simple microscope in normal estimate. Let us look at it when it is not in normal estimate. Not in normal use. When not in normal use, we expect the final image to be formed at a near point at infinity, And if it is to be formed at infinity, where are we supposed to place? The object? We talked about that we are placing the object at the focal plane, at the principal focus, like that. Because when light comes, it will be incident on that other lens, then let it go through F, like that. Then look at this. If these distances are the same, this other thing will be parallel, they will never meet. But even when we try to extend it to this other side, they will not meet. So we expect the final image to be formed at infinity. We are forming the final image at infinity. We don't know where. So it would mean that if this other height was the height of the object, I want to look at the angular magnification, of which angular magnification becomes alpha prime over alpha prime over alpha, where alpha prime is the angle subtended by the image to someone's aided eye, and alpha is the angle subtended by the object to someone's unaided. The other one is aided, this one is unaided. So let us start with alpha. I told you that with alpha, extract it out. Because for it will never change, that will be a D, because you are using your naked eye to view a particular object with all its details seen clearly, meaning that this other one becomes a D. A D becomes the least distance of distinct vision. I forgot to tell you that in normal people, it is always 25 centimeters. When you get your ruler and measure off 25 from your eye, where you put your object, the details will be seen clearly. It varies with younger ones and older people, but a normal adult person would be having that being 25 centimeters. Beyond 25, it becomes a far distance. Even before 25, it becomes a far distance, because we said that a far distance is that distance beyond which or below which the object's details cannot be seen clearly, like that. So that means that if I have a tan of alpha, that tan will be h over d, like that. And for small angles z, what is true with small angles, the tan of alpha approximates to alpha, meaning that alpha is h over d. We keep this because this is for unaided. You are using your naked eye to see, like that. Now when we go back to the instrument, that's when we talk about that alpha prime, the aided now. So I told you extract that for unaided. That's when you will not be confused. Yes? Extract that of unaided, put it there, then use the instrument to find the aided. With the aided eye, this is what is seen. With the aided eye, I'm looking at tan. Use just the instrument. The tan of alpha prime becomes just have h, like you see it here, and then over which distance? This distance is f, because this is the focal length, like that. So it would mean that I just have over f. That means that for small angles, at the tan of alpha prime approximates to alpha prime, like that. It would mean that alpha prime becomes h over f. So you have magnification now, angular magnification being alpha prime over alpha. I'm getting here, see, the alpha prime is h over f, and the alpha is h over d, like that. So that one would mean that we have d, because we shall be having h over f times d over h. So it will mean that the angular magnification now becomes d over f. This one now becomes the angular magnification in a simple microscope, when not in a normal guesstimate. Simple microscope when not in a normal guesstimate. That one pushes us to compound microscopes. Compound microscopes. Compound microscopes. Still in compound microscopes, we shall look at them when in normal guesstimate and when not in normal guesstimate. But maybe on the introduction part of them, for them, like we had converging simple microscopes with only one converging lens. With compound microscopes, for them they have two lenses. One of the lenses is called the objective lens, and the other one is called the eyepiece lens, eyepiece. So maybe in the introduction, for them they all objective one, eyepiece lenses. Yes, I think that is the only difference between compound microscopes and simple microscopes. With compound microscopes, for them they have got two lenses, an objective lens and then the eyepiece lens. I want to look at these compound microscopes when in normal guesstimate and when not in normal guesstimate. Still, nothing changes. When in normal guesstimate, we look at those other microscopes that the final image will be formed at near point. I want to say when in normal use, that is when in normal adjustment. Yes. when in normal use. Its arrangement is very simple. That if that is this would be the arrangement. We first of all give us an objective like that. Always the object faces the objective. I want to put my object around there. It will be facing the object. This is the issue. The object will face the objective, like you can see. We first of all form the image of the objective. Let us form the image. This other objective, this is the objective lens. As I said, it has a focal length f naught. It is going to help us form a particular image somewhere. That is, this is f. I always call it f naught. Like that. Like that. It is forming a particular image somewhere here. The objective is forming a particular image here. This is the image being formed by the objective. The eyepiece will be put somewhere such that it does what you want. Do you want to form the image at infinity? Do you want to form it at a near point? So the eyepiece is there to do whatever you want. This is the eyepiece. It has got a focal length Fe, like that. The other one was F naught. Now, what is your question? That you want to form the final image at infinity, at near point. No use near point. If you want to form it at a near point, we discussed and said that whenever the image is to be formed at a near point, it would mean that the object must be put in between the principal focus of such a lens that wants to form the image and its pole. So where is the lens that is supposed to form the final image? It is now the eyepiece. It is using the image that was formed by the objective as its object. It is using the image being formed by the objective as its object, such that it can form a final image somewhere, or at infinity, or at a near point. That is what we can say. So we shall ask people, because this is where this is where we put the mark. Do students know where this object must be? If I put here point A and then point B and then point C, where exactly will I put my FE? I'm supposed to put the FE at C. Why? Just because I want to have what I'm calling my object now. I want it to be in between the principal focus of the lens that it claims to be the one to form the final image, and then its pole. That the object I'm using must be in between the principal focus of this other lens and then its pole. That is when I will be able to form an image at a near point. Yes, I can never put it here because I don't want. When I put it here, it would mean that I want it to form. I want the final image to be formed at infinity, like that. Now, what happens? That would be the issue. The next thing is just need to have a particular line that J is the tip of. Just the tip of that other object, like that. And then you have these, because you want to converge, just bring them, just get a ruler, let them come and converge in this other line. Just simply as that, like that. Because they are converging in this other side, you put a mark also here. because they are converging this side, it would mean that the other side they had diverged. See? You can't put parallel here when they are converging the other side. So where they converge, just come and have your image being drawn. This is the image being formed. This is the image being formed by this other lens. This lens has used the image that was formed by this objective as its object to give us a final image. Like that. Magnification, maybe separation between the lenses, like that. The distance from here up to here becomes D, because that would be the near point. Yes, the distance between the lens, this okay, that will now be the distance in between the lens and where you're forming your image. Where the image is a near point. Because this is a near point, then this other one becomes, because this is a near point, then that one becomes a D. Like that. With this other one, you can name it V0 as the image of the objective. No problem with that. I want to have this one being H, that height there. I want to have this other one maybe being H prime. Like that distance from there to there. This image is always called an intermediate image. Students, you can have this other image being intermediate. The image that is formed in between the objective and the eyepiece becomes an intermediate image, like that. I want to have this other height now being H. Height being H. See? Now they will be telling you to derive the angular magnification, because the angular magnification is alpha prime over alpha. You want to claim this other here to be alpha. Claim that to be alpha, and then the other one, I claim that other one there to be alpha prime. But like I told you, if I'm dealing with unaided, this is unaided eye, still you just come and extract out to this being alpha, like that, and the height here being H. And because you are viewing an object at a near point, still name that D, such that you simply just have the tan of alpha being equaling to H over D, like that. And for small angles, this other tan alpha approximates to alpha, such that alpha becomes H over D, and we keep that. That one does not even change. That one doesn't change. Now, how will you find alpha prime? The tan of alpha prime, just look at it from the instrument here. Alpha prime, it gives us opposite, which is H, and then adjacent, which is a D. Capital H over D. So someone wants to find the magnification. That magnification will be alpha prime over alpha, giving us H over D, and then divided by H over D, yes, small h over D, giving us H over D over H. The magnification now, you people, becomes H over D, over H, like that, capital H over H, giving us C. Now look at this, I can write this as H over H prime. I want to bring in an intermediate. If you can recall from chain rule, I can write this as this, the H over H prime times H prime over H, because the H prime can simply cancel, and that one tells us that, that would be the chain. It's like as if I have not done anything, like that. Now when you look at h over h prime, it is a magnification being caused by an IP, a particular eyepiece. Let us check the diagram. So this is the image, then this is the object. So image height over object height gives us a magnification, but being caused by the eyepiece, like that. Then h prime over h is also magnification, but being caused by the objective. Again, check the diagram and see. But this is object height, image height. So h prime over h is a magnification. Those are linear magnifications of such lenses. So it would mean that the magnifying power now becomes ME times MO. But ME, I can have it as V over F minus 1. Then, which F now? FE. V over F minus 1, which F of the objective. The image distance of the objective here, the image distance of the objective is V naught. So instead of writing V for me, I will just come and write V naught. This is a D. If you can see from the diagram, it is actually D. So instead of talking about V, I want to talk about D. So this one now becomes the angular magnification of a simple microscope in normal estimate. That one pushes us to simple compound microscope. Not in normal estimate. Not in normal estimate. Here we expect the image to be formed at infinity. So if this is the objective, like that, and you have your object here, we expect, of course, this would be F naught. Oh, there are some things that I did not discuss. Somebody may tell you to obtain the separation between these other two lenses. The distance from here up to here becomes a U, an object distance, but for the eyepiece. So it would mean that the separation between the two lenses, separation between these other two lenses, separation, that is separation S, will simply be V naught plus U naught, UE. V naught plus UE becomes the separation. The moment in calculations, we shall calculate in calculations, the moment you find the V naught and then you find the UE and find the UE, and then you just add them and get the separation between the two lenses. It is also commonly asked like that. So it would mean that if I have that, I have formed an intermediate image. The distance from here up to there becomes V naught, like that. So I have the eyepiece here. Because I want to form the final image at infinity, where will the object be? Because now this one is now becoming my object. The image formed by the objective, the image being formed by the objective becomes the object of the eyepiece lens. So the eyepiece lens uses it to either form a final image at infinity or at a near point. But this time around we want to form it at infinity. Yes? Where can we put the FE of this other lens? Is it somewhere here at A? Is it at B? Is it at C? We are putting it at B. We are putting FE at B. Why? That every time I want to form an image at infinity, then the object must be placed at the principal focus, or in the focal plane of a lens that claims a lens that claims to have a lens that claims to form a particular image at either infinity or at a near point. So we simply have a line here like that. Then we have this. Because we want to form at infinity, these ones will be parallel to that line. The others we are converging, so they will be parallel lines like that. So it will mean that we just need to come and have these. These ones are continuous, the other ones are dotted, because we are forming virtual images like that. So simply have that. And everything. So just let me have H here. This is alpha. I want to have this being alpha, of course. And then talk about the C being alpha prime, like that. So let me just have this one being H. I want to derive the magnifying power. Talk about the magnifying power. Just have a tally of alpha, just alpha prime. This is unaided. The tally of alpha and now simply becomes, because if I just come and extract it out, this is a D, the other is H. I'll be having H over D. So the alpha becomes H over D, like that, for small angles. But now when I move on to the other, we just have the aided. With the aided, just talk about the time of alpha prime. The alpha prime becomes H over the distance from here up to here is FE over FE, like that. So the alpha prime now becomes H over FE. So magnifying power now becomes alpha prime over alpha, getting us H. Alpha prime over alpha, getting us H over FE, and now divided by H over D. So this other gets us H over FE times D over H. Like that. So, this is H. This is H prime. I want to have this other one here being H prime, H prime, H prime. So it would mean that the magnification now becomes H prime over H, then times D over FE. This one is a linear magnification of that one now becomes a linear magnification of the objective. That is linear magnification of the objective M0. So I can simply have V over F0 minus 1 times D over FE. With calculations, you feed in that D being a negative 25. This one, when you feed in negative 25 centimeters, like that. So the V here is a V0 for the objective, minus minus 1, I'll be coming with d over fe. The next time we meet for the next episode, we shall be able to make calculations on both the simple microscopes and the compound microscopes. Thank you so much.